Hello everyone, in this video let us study about the amplitude modulation and the modulation index. That is nothing but the general expression of this amplitude modulation and the modulation index. So in my previous videos I have explained you about the modulation, like what modulation exactly is, and I have also demonstrated with an experiment, like I had taken a paper and then I had kept something inside it and I tried to make it reach the corner of the room. So that is where we studied about the modulation. So all the sinusoidal carrier modulations, they are come under continuous wave modulation. So in that we have two types. One is amplitude modulation, another one is the angle modulation. In angle we will be having the phase modulation and the frequency modulation. So let us study about the amplitude modulation. So what is this amplitude modulation? It is the process in which the amplitude of the carrier is varied in accordance with the modulating signal. So one thing I will say, that for the modulation to take place, we require two signals. So that is, one is the message signal and the second one is the carrier signal. Okay, so this message signal, this is also called as modulating signal, or it is also called as baseband signal. Okay, baseband signal. I have told you that the baseband signal, the frequency spectrum of that, it will be centered about the origin. So this is the frequency spectrum of the message signal or the baseband signal. Okay, we can have any shape. I am taking a triangular one here. Carrier signal is a high frequency signal. Okay, and what we studied is this message signal, it was superimposed or impressed on the high frequency carrier signal so that it could reach longer or it could travel longer distances. That is where the modulation takes place, right? So message signal will be impressed on the high frequency carrier signal so that it can travel longer distances. Okay, so now we were studying about the amplitude modulation. So in telephony, like if you want to transmit this speech signal on the microwave links, okay, for that what happens, see, the transmission frequencies must be increased to the gigahertz range for transmission over the channel. In the lecture that is where I was covering the need for modulation, I told that the frequency spectrum of this message signal was translated to some other frequency. For example, if the carrier's signal has the frequency FC, then what happened? The frequency spectrum which was centered about the origin, it went or it was translated to a frequency FC. Okay, so it was like this. This was my message signal. This is FM and this is minus FM and this is 0. What happened is it got translated. Okay, it got translated something like this. One second. Somewhere like this. Okay. FC. This is minus FC. FC plus FM. And this is FC minus FM. Okay, so this is what the frequency translation is. From 0, it went to FC. Okay, so that is frequency translation. This is C. Normally what happens is speech means it will be like 20 hertz to 20 kilohertz. Various kilohertz, various gigahertz. Okay, so it has to be transmitted to, or it has to be increased to the gigahertz range for the transmission over the channel. Okay, so message signal and the carrier signal. So now let us see the general expression for the amplitude modulation. Okay, general expression will be S of t is equal to AC into 1 plus Ka m of t. Then we have cos omega ct. Okay, where AC, it is the amplitude of unmodulated carrier. Then we have Ka, which is amplitude sensitivity of modulator. Okay, this Ka is required for the generation of the amplitude modulated wave. We will see that, or how it generates the S of t, that is nothing but the amplitude modulated wave. Then omega c, this is the angular frequency of the carrier wave. So omega c, okay, so this can also be written as 2 pi fc, where fc is the frequency of the carrier wave. So this is the general expression for the amplitude modulated wave. We can also write in another form, that is AC plus m of t cos omega ct. Okay, AC plus m of t cos omega ct. So this is the second type of representation of the amplitude modulated wave. So remember, this message signal m of t, this is the message signal, that is nothing but the baseband signal, low pass signal, or it is also the modulating signal. Okay, this contains all the information, whereas the carrier signal c of t, which can also be written as AC cos omega ct. Okay, if you want, I can also write the phase of this carrier. Generally, we are going to consider phase as 0 here. Okay, so we will be writing AC cos omega ct, which is a carrier signal. Okay, this is the modulating signal. This carrier signal, it does not contain any information. Okay, all the information is consisted in the message signal, that is m of t. So now we can see here, this I can write it as E of t, which is nothing but the envelope of the amplitude modulated wave. Okay, envelope. So here, this can be considered as E of t, that is the amplitude of the amplitude modulated wave. Okay, so that can be written separately. E of t is equal to AC into 1 plus Ka m of t. This is my envelope. This is my envelope of amplitude modulated wave. Now, there are conditions here for the envelope, okay, to follow the message signal, means the shape of the message signal. Two conditions should be satisfied. One is the carrier frequency should be greater than FM, okay, and the second one is magnitude of Ka m of t, that should be less than 1. If these two conditions are satisfied, the envelope, okay, shape will be similar to that of the message signal. Okay, if Ka m of t greater than 1, then what happens? There will be over modulation. Over modulation. Let us see that also. What is this over modulation? What is the critical modulation? What is under modulation? Okay, what is this modulation index? And how this amplitude sensitivity of the modulator is related to the modulation index. Okay, so in the amplitude modulation, once again we will see that there are different ways of amplitude modulating the carrier signal by the message signal, and those are 4 types. One is a conventional double sideband AM. Another one is the same thing, but in that we are going to remove the carrier signal. I already said that the carrier signal does not contain any information. So if I am suppressing this carrier, there is no loss of information. Okay, then has a single sideband amplitude modulation. That is obviously what happens is you will be having upper sidebands and the lower sidebands, which you will be seeing in the next videos. Okay, upper sideband and the lower sideband. In that, either we will be transmitting the upper sideband or we will be transmitting the lower sideband. Next is the vestigial sideband. We will see all these 4 types of amplitude modulation. Okay, so see here, I have already told you about the general expression, and another one I have told you, S of t, that is equal to AC plus m of t cos 2 pi fct. This is another general expression for the amplitude modulation. So you may get any kind of expressions, okay, as your question. So you should be aware of both these expressions. So Ka is amplitude sensitivity, m of t is your message or the modulating of the baseband signal, and Fc is the carrier frequency, and totally AC 1 plus K m of t, that will be the envelope of the amplitude modulated wave. So here, see, if this is my message signal, I am taking message signal as my sinusoidal signal only. Okay, so this is m of t, which is equal to am cos 2 pi fmt. Okay, so this is my message signal. So this is my carrier signal, that is AC cos 2 pi fct. So here it will be following something like this. This is when modulation index is less than 1. I will tell you about the modulation index. There are different types. Okay, so here this is the shape of the message signal, right? This is the shape of the message signal. It continues like this. This one will be the mirror image. Mirror image. So this is the envelope. This is the envelope of the amplitude modulated wave. And this, what is inside? This is a carrier wave, right? C of t. Okay, and one more thing, you know, suppose I'm taking this signal and another one I'm taking this one, which has higher frequency. Obviously this is higher frequency, because if I consider this as the duration t, f is equal to 1 by t, right? So if this is my 10 seconds and here if the duration is 1 second, okay, here it is 1 by 10, it is 0.1 hertz, and here it is equal to 1 hertz. So you can see that 1 hertz is greater than 0.1 hertz. So the frequency of this signal is greater than the frequency of this particular signal. Okay, so that's why we call this carrier signal as a high frequency signal. You can see here how close it is, right? So this is the carrier signal. This is the envelope. Okay, so the envelope is following the shape of the message signal. Okay, so next, what is this modulation index is? It is a measure of how much the modulating signal modulates the carrier signal. It is a measure. Okay, depth of modulation. They will be considering depth of modulation. So here we can say, if I consider MA as my modulation index, that will be equal to, okay, that is the ratio of the amplitude of the modulating signal to the amplitude of the carrier signal. Amplitude of modulating signal to the amplitude of the carrier signal. So here I can write it as maximum of m of t divided by AC. So suppose if my m of t is am cos 2 pi fmt, what is the maximum value of this? You know that cos, it will be from -1 to 1. So the maximum value of the cos will be equal to 1. So maximum m of t will be equal to 1 into am, that is am by AC. So this is my modulation index. Ratio of modulating signal, amplitude of modulating signal to the amplitude of the carrier signal. Okay, so in this general expression, S of t is equal to AC 1 plus Ka m of t cos 2 pi fct. In this case, I can consider the modulation index as Ka m of t max. M of t max. So this will be my modulation index. Okay, from this what I can see here, for suppose m of t is same thing, am cos 2 pi fmt, ma will be equal to Ka into am, and we know that is also equal to am by AC. So if I take like this, Ka will be equal to 1 by AC, means here it has a volt, so this unit will be equal to per volt, because AC is the amplitude which has a unit of volt. Ka will be per volt. Ka is equal to 1 by AC. You can use this expression only when Ka is not given in your expression. Okay, if Ka is given in your expression, then you have to use Ka itself. Okay, so this is an important point that you have to note it down. Okay, so S of t is equal to AC plus m of t cos 2 pi fct. This is another general expression. Here you do not have any Ka or amplitude sensitivity. So you can use am by AC in this particular expression. Okay, so now see this An audio signal 50 sine 2 pi 1500t amplitude modulates 60 sine 2 pi 10 to the power 5t. The modulation index will be, and you have already seen it is AM by AC. So what is AM? It is 15, AC is 60, 1 by 4 that is 0.25 which is equal to 25%. 25% will be the answer for this. Okay, so next you can see, actually I will be telling you something else also. So this modulation index, I said it is AM by AC. This modulation index, if it is less than 1, it is under modulation. MA is equal to 1, this is called as a critical modulation. MA greater than 1, this is called as over modulation. In this particular case, we can't recover our message signal. Okay, in over modulation case. And MA less than 1, that means AM by AC less than 1, which is nothing but AM less than AC, which means AC minus AM greater than 0. Okay, AC minus AM greater than 0, this is the condition for MA less than 1. So, I will tell you something else here. See, this is my AC. You know AC into 1 plus Ka M of t. This is my envelope, right? So, if I take M of t is equal to AM cos 2 pi FMT, okay, 2 pi FMT, this will be AC into 1 plus Ka into AM. So, Ka into AM is your modulation index. So, I can write it as 1 plus MA, right? So, this is AC 1 plus MA. So, here I can write AC 1 plus MA here and AC 1 minus MA. MA is AM by AC. So, this should be AC minus AM, right? This is AC plus AM. So, here I can also write it as AC plus AM. This another one will be AC minus AM. This is my 0. So, AC minus AM, see previous condition. If you have not understood, I will tell you once again. AC into 1 plus Ka M of t, that is the envelope, and K M of t if it is AM cos 2 pi FMT. Okay, so this will be 1 plus Ka into AM cos 2 pi FMT, right? So 1 plus Ka into AM, okay, here what I can consider is AC into 1 plus MA. 1 plus MA, so this I will be considering it as 1. AC into 1 plus MA. Okay, so here MA is equal to AM by AC, which we already know. So AC 1 plus AM by AC, so this should be equal to AC plus AM, right? So that is one thing. Another one is when cos 2 pi FMT, that is equal to minus 1. So that time you will be getting AC minus AM. So this is the maximum value, this is the minimum value of the envelope. So for MA less than 1, I said AC minus AM is greater than 0. That means minimum value of the envelope should be above the 0 line. That means should be above here. This is the case. So here I am going to trace something like this. If I take the mirror image of that, I will be getting something like this. And inside that, we will be having the carrier signal, right? Here I will be having the carrier signal. Okay, you can draw it. You can continue it. Okay, so this is AC plus AM. This is AC minus AM. From this is my A max or E max, whatever you call it as. This is my A minimum. From this figure, I can find out the modulation index. I can find out the modulation index from that particular figure. How? A maximum minus A minimum divided by A maximum plus A minimum. So let me substitute that. AC plus AM minus AC minus AM divided by AC plus AM plus AC minus AM. So this is 2AC. Above you will be having 2AM. So AM by AC. What is AM by AC? This is the modulation index. So from this figure, how do you get to know? If you know this particular value and if you know this particular value, you can find out the modulation index. And here we have another problem like that. What will be the modulation index of the AM wave shown in the figure? So this is my AC plus AM. This is my AC minus AM. So here what happens? 13 minus 7 divided by 13 plus 7. So this is 20 and this one is 6. Okay. So here you can write 0.3. This is my modulation index. That means depth of modulation is 30%. Okay. So 13 minus 7 divided by 13 plus 7. 13 minus 7 divided by 13 plus 7. So this is 6 divided by 20. So this is equal to 0.3 and the depth of modulation in percentage, that is 30%. So this is how you can find out the modulation index from the figure. Okay. So in the case of overmodulation, MA is greater than 1. That means AM by AC greater than 1. AM is greater than AC. Okay. So this is the condition for the overmodulation. Okay. So we will be studying about the single tone modulation, multi-tone modulation in the next lectures.